Hello students, and welcome to our lesson on one-step equations. What we're going to be doing on this one is figuring out how to verify a solution to an equation. That way when we get one, we can check if we actually did things correctly. We're going to learn how to identify the three major types of equations, and then we're going to talk about how to solve when there is just one step. So essentially we'll be covering moving terms as well as making coefficients one. So it'll be a lot of adding, subtraction, multiplying, and dividing. You know, all the math operations we love. So let's get into it. At the top, what is an equation? Well, an equation is a statement that states two expressions are equal to each other. So when we look at 3x plus 5 equals 11, that is an equation. And what it's saying is that 3x plus 5, the expression on the left, is equivalent to 11, which is the expression on the right side. Now, in this example, 11 is just a constant. It's just a number. But that's not always going to be true. As we build up our knowledge base, we're going to have more and more complex equations in math. And eventually we'll have full-blown expressions on the other side that could have distribution or really any number of steps involved to simplify it. For right now, though, and for this class in general, we're only going to be working with linear equations. Okay, so you don't have to stress too hard in this one, but just know that this does expand as we go deeper into mathematics. All right, so we have two expressions set equal to each other. Great. What do we do with that? Well, our goal is to isolate the variable. And we're going to isolate the variable by using what are known as inverse operations. So we've learned how to add, subtract, multiply, and divide, but those all have inverses, as we saw in topic 10 when we were going over useful properties. So what we're going to be able to do is undo whatever's happening to x in the expression. So to get the variable alone, you just sort of get rid of everything that's around it by undoing all of those things. And what it's going to look like when we get down to an actual answer is x equals a number. So right there, I'm just writing the pound symbol. But our goal is to get everything we do to look like x equals a number on that other side. Because then what we will have is called a solution, or at least a potential solution. A solution of an equation is a value that makes the equation true. So let's look back at 3x plus 5 equals 11. If I plug in x equals 2, I would have 3 times 2, because 3x, and if x is 2, 3 times 2, plus 5. That is 6 plus 5, which is in fact 11. And so x equals 2 would be the solution to 3x plus 5 equals 11. It is a value for the variable that makes the equation true. And to check when we solve for an x value, if we actually got a solution, we're going to do exactly what I did in black over on the side there. We are going to substitute that solution in to the equation for the variable and see if both sides are equal to each other. Another word for substitute, by the way, you might have heard is just called plugging in. So we're going to plug in our answer and see if it works. All right, example 1 here. Is x equals 4 a solution of x plus 3 equals 7? What we are checking is whether or not when we plug in 4 for x, if we get a true statement. So what I do is take this number 4, and wherever I see an x, I'm going to write parentheses with a 4 inside. And you might be thinking to yourself, hey, those parentheses are not at all necessary here, and you're correct. However, in number 2, you're going to see why we need parentheses. So just bear with me, and please get in the habit of always putting parentheses around the number you plug in. All right, so now we're going to simplify. We have 4 plus 3 equals 7. Those parentheses, as noted earlier, don't do anything. And so this just becomes 7 equals 7. And that's true. This is a true statement. So x equals 4 is a solution. And that's all you have to do to verify if your solution is valid. Take that number you get, substitute it in for x, and see if the statement is true. So now we're going to see what it looks like when it's not true. So number 2 says, is -5 a solution of 2x equals 12? First things first, is -5 a solution? This is shorthand notation for is x equals -5 a solution of 2x equals 12? So just know when we just throw the number out there, we can use context clues right now to assume that that -5 represents x, but we might have other variables in the future, so we just got to be careful, okay? That one's just shorthand though. Is x equals 5 a solution? So now we're going to take -5, plug it in for the x right there. That is going to give us 2 multiplied by x, okay? 2x is 2 multiplied by x. So I really need these parentheses right now, because if I don't put that -5 in parentheses, it just says 2 minus 5. 2 minus 5 is not what we want. We want to be multiplying 2 times -5, because 2 times -5 is -10. 2 minus 5 is -3. That's a completely different result. So on the left side, 2 times -5, we get -10. On the right side, we get 12. Are those equal to each other? No, of course not. So what we're going to do is say that this is a false statement. -10 does not equal 12. And since we got a false statement, x equals -5 is not, okay, not a solution. All right, so we saw one where we got a true statement, one where we got a false statement. And you're going to sort of stop seeing me do that, but because I know that my answers are right. Okay. It's a little bit of like, experience earns you the ability to skip steps situation. At my point in my mathematical career, when I solve an equation, I don't generally have to plug it back in. However, we are in a prep course for college mathematics. The whole purpose of this course is to get you ready for the higher level math class. So we absolutely need to make sure that we are always checking our solutions. All right, we cannot just get an answer and move on with our lives. We are still at the beginning stages where we are practicing and learning. So plug them back in. On a test, you can guarantee that you get an equation solving question correct by just checking your answer, and then you don't have to stress over it. So always check your answers. That's the moral of that story. Now, let's classify some types of equations. We have 3 types: conditional, identity, and contradiction. And they are sometimes difficult to recognize right away, but they are always easy to recognize once you have solved. So when we get down to the examples down below, you're going to see that they are kind of pre-solved for us, because once you solve an equation, it's very obvious what type you have. But when you look at the equation at the beginning, it's not so clear. All right, let's look at conditional first. We have x plus 5 equals 9. If I were to solve this equation, which we don't know how to do yet, but just bear with me here, I would get x equals 4 as my answer. Notice that I have one solution. So I'm going to call this one distinct solution. Okay, distinct just means that you can tell it apart from other solutions, but since we only have one, that doesn't mean much for us here. Another word you might use is the word unique, which just means special or unlike the others. So it stands out. But anyway, we have one solution. So a conditional equation is called conditional because it's true under the condition that x equals 4 in this case. So that's going to be the next thing I write down. After one distinct solution, we're going to say that this is true under the condition that x equals 4. If x equals anything other than 4, this equation is not true. So it is only true conditionally. The next one is an identity. This is going to be true all the time. So when I go up to people, I say, hello, my name is Christopher, because that's who I am. That is my identity. So when I think about the word me and I think about the name Christopher, those are the same to me. They're referring to the same individual because that is my identity. So the key to an identity is that we have the same thing on both sides. On the left, we have 2x, and on the right, we have 2x. And what are we doing to that 2x? Well, on the left, we're adding 6, and on the right, we're also adding 6. So everything that's happening to x on both sides is exactly the same. Okay? When we try to solve an equation like this, we are going to get a true statement. We're going to get something that looks like 0 equals 0 or 7 equals 7, something that is just always true. And because it's always true, there are actually going to be infinitely many solutions. And in this case, what that means is that every value of x makes this equation true. No matter what you plug in, it will be a true statement. Okay, so we call this being an identity because the sides mirror each other. One side is the other side. They are the same. And then underneath, what I'm going to write is that this equation is always true, or this equation is true for every value of x. So there is no condition. We don't need x to be anything specific. This equation just is always true. And again, I didn't write it down. Let me write it down now. What we're going to get to is something that looks like 0 equals 0. We will get a true statement when solving. And when you get a statement that's always true, you know that you have an identity. The next one is the opposite. It's a contradiction. This is like a lie. Okay? If I try to solve the equation x plus 2 equals x plus 3, I'm eventually going to get to a place where it just says 2 equals 3. That is simply not true. Okay? So we're going to get to a false statement, and that false statement means there is no solution. Now, no solution is kind of wordy. I don't like writing all that out. So we have a nice convenient symbol for it. If you draw a 0 and put a slash through it, that just means no solution. Okay? Technically, it means the empty set, which means that the set of solutions is empty. There's no solutions in the set of solutions. So therefore, there just is no answer. So we call this type of equation being a contradiction because it contradicts itself. It gives us a false statement such as 2 equals 3, which again is just simply not true. And so this equation is never true. Right, so we have three types. Conditional equations are true under the condition that x is a certain number. Identities are always true, so x could be any value and it still works, so all x's are solutions. And the last one is contradictions. This is where you get no solution because you stumble upon a false statement. So there's no value of x that will make a contradiction true. And by the way, just in case my answer keys end up showing it to you at some point, for an identity where we have infinitely many solutions, sometimes the way those solutions will be written is using a fancy capital R, where it's 2 lines down with an R drawn over it. And that means all real numbers, which right now we don't need to dive too deep into that, or any deeper into that, I should say. But just know that if you see that fancy R, that means that every value is a solution. Every number works. So there are infinitely many of them. All right, down below, we're just going to recognize a few of these and just label them as conditional, identity, or contradiction. In the first problem down there, we have 5 plus x equals 12. When we try to solve that, we would get x equals 7. Notice there's nothing wrong with this. This is what we expect. X equals a number, and so this is a conditional statement where we say this equation is true under the condition that x is 7. And from the beginning, the way I can tell, which this is not an amazing way to tell, okay, looking at the answer is the best way, but from the beginning, we can use a little intuition and say that x only shows up on one spot. When x is only in one place, we're going to be able to move around the numbers and get x by itself. So whenever x only shows up once, it's going to be conditional. But again, I encourage you to not rely on that. Rely on what the answer looks like. If it says x equals a number, that is a conditional statement, true under the condition that x is that number. Now, if we look directly below it, we have 3y plus 7 equals 3y plus 7. The giveaway that this is going to be an identity is the fact that the left side looks exactly the same as the right side. When we go through the steps to solve, we're going to end up with 7 equals 7 in this case. And notice that that is a true statement. So this equation is not true under the condition that x is any particular number. This equation is true no matter what value the variable has. And in this case, I got to be careful. The variable is actually y. So we would say that y can be any number. So this is an identity. And we would say that y could be any number. There are infinitely many values of y that will make this equation true. Number 3 down there, we have 4z plus 2 equals 4z minus 5. If we try to solve that, we're going to get 2 equals negative 5. Notice that that is not true. 2 does not equal negative 5. That is false, and more specifically, that is a contradiction. So this equation has no solution. And a way you can recognize that from the beginning, notice that we see 4z show up on both sides, so the exact same number of the variable, but they have different values being added or subtracted from it. That's generally a giveaway that it's not going to work out, and it's going to have a contradiction in it. Okay, number 4, 10 minus w equals 6. Notice there's only one w in this equation, so we already know that this is going to be conditional, but then when you look and see that the solution is w equals 4, well, that's exactly what we expect from the equation. W equals a number, so this equation is true under the condition that w is 4. Number 5, I threw the distributive property at you in the middle of a lesson. Look at this. If we distribute 2 to the a plus 5 in parentheses, we would get 2a plus 10. And look at the other side of the equation. It just says 2a plus 10. So they didn't look exactly the same at first, but by doing a little bit of algebra, they both now say 2a plus 10. And you can see that when we simplify this, we'd get something that is true, like 10 equals 10, but we didn't even have to go that far. The fact that the beginning parts look exactly the same means that this is going to be an identity. One side exactly matches the other side. Oh, not identify, identity. It would help if I could spell. That's why I teach math though, guys. Number 6 down there, 7b plus 1 equals 7b minus 3. This should remind you of number 3, where we have 7b on both sides, but something different is being done to it. So if you start with 7b in both cases, but you do different things to that 7b, you're going to end up with different results. And that's exactly what happens. We end up, when we solve, with 1 equals negative 3. That is false. And again, more specifically, we call that being a contradiction. So there is no solution to number 6. All right, we're going to get a little bit away from this classification part. And instead, what we're going to focus on is actually solving one-step equations. So in order to do this, we got to add a little bit of terminology to our tool belt, so to speak. So solving one-step equations, the goal is to isolate the variable, just like we said earlier. We want to end up with x equals a number. But now we got to actually do the solving. Okay, in the last little section, we had the answer done for us. Now we have to go find that answer though. So to solve for the variable, we are going to use the inverse operations I mentioned earlier. But we can't just do this in one spot. So we need to think of an equation like a scale. I don't know if you guys have ever seen a scale like this, because maybe I'm a little old compared to you guys. Imagine a teeter-totter. I think we've almost all seen that, where you have a plank or something balancing over what is called a fulcrum. Okay, the fulcrum is the center point. Now imagine you have little Susie on this side. I'm a terrible artist, so please ignore my stick figure drawings. But then little Jimmy over on this side. And the idea is that the seesaw only works if both sides have the same amount of weight on them. So we want both those humans to be the same size, preferably. That way we can balance out our teeter-totter. An equation is a lot like this, where in order to keep the balance, we have to have the same thing on both sides. And so that's all we're going to be trying to do, is keep the balance as we go through each of these inverse operations. So whatever we do to one side, we will also be doing to the other side. And I'm going to show you guys how to draw a line to make sure you stay organized. And last thing is just that solutions can be verified by plugging them back in or substituting them into the equation. All right, we're going to learn how to do two things right now. Hands down, the most important things I need you to take away from this lesson are these next two small little sections. One is about moving terms, and one is about making the coefficient of the variable 1. When I say, how do I move this thing to the other side in class, because you're going to hear me say it all the time, you need to reference this section in your brain. Okay, when I say move terms, I'm talking about exactly what we're about to do. So let's look at it. In order to move terms, we are going to use the additive inverse That way we can move a term to the other side of the equal sign. So the way this works, if a plus c equals b, then it's also true that a is equal to b minus c. So notice that the letter c was positive on the left, and then it moved and became negative on the right. So then the question is, how do we get it there? Well, the first thing I'm going to do is draw a vertical line through my equal sign. And you guys are right now thinking, what? Why are we drawing lines? Well, it's to keep us organized. Okay, imagine this vertical line is the same as the center fulcrum point on my teeter-totter. I need to keep the balance on the left and on the right. Now, my goal in this problem is to get the letter A by itself. All right, I want to get A all alone on the left side of the equation, but right now it's A plus C on the left. So I have to move that C. That's all we're doing right now. We're moving C. If I could, I would literally just grab C and move it to the other side. If it was an object, I'd just place it somewhere else. But with algebra, we have to use inverse operations. So notice that right now it's A plus C. Plus C. We want to do the opposite of plus C. And the opposite of plus C is minus C. So what I'm going to do, right under where it says plus C, I'm going to write minus C. But now the balancing part. I am not allowed to just write minus C on the left side. That's like putting a second little human on the left side of the teeter-totter. It's going to weigh it down. It's not going to be balanced anymore. So I need to also put a minus C on the right side. Then notice I draw a little horizontal line to keep myself organized. On the left side, the plus C and the minus C cancel each other out to just give me 0 right there. And I could write plus 0, but that gets very messy. So instead of on the left side writing a plus 0, which is what we technically have, we just don't write the plus 0 part. All right, we're just going to write the letter A there. And to be clear, the letter A is there because I dropped the A down from the previous step. The C's canceled each other out, but that letter A is still there. Now, my vertical line is my equal sign, so I'm just going to put an equal sign through it. And on the right side, it says B minus C. Those are not like terms. B and C are different variables, so I cannot combine them. I just leave them as B minus C. But now look at what I have. I have A on the left is equal to B minus C on the right, and that's exactly what I was supposed to get based on this formula. A equals B minus C. So what I need you guys to take away from this is that in order to move that letter C to the other side, I had to subtract it from both sides. Now, what we're about to do is the same thing, just with a different operation. So if you look slightly to the right, we have A minus C equals B. And again, we want to move C to the other side. Because it says A minus C, I'm going to do the opposite of minus C. The opposite of minus C is plus C. Okay, that is the additive inverse of minus C. So I add C to both sides. Notice that on the left side, negative C and positive C cancel each other out. So again, I could write plus 0 there, but no need. Okay, plus 0 doesn't do anything, so we're going to leave the 0 out. We're just going to drop down this letter A that was not affected. And then on the other side, we have B plus C, which again cannot be combined, so we just leave it as B plus C. So we effectively moved that negative C we started with to the other side by changing it into a positive. Okay, now we're going to do this with actual numbers. So our goal in each of these is to get x by itself. In number 3, we have x plus 7 equals 12. The first thing I'm going to do is draw a vertical line through my equal sign. This just keeps me organized. And then now I'm going to isolate x. X right now has a 7 being added to it, so I'm going to do the opposite of adding 7, which is subtracting 7. Then I draw a horizontal line to keep me organized. Notice I wrote minus 7 on both sides for balance. When I simplify, the plus 7 and the minus 7 cancel each other out to give me the additive identity of 0, which I just don't have to write. And I'm left with x is equal to 12 minus 7. But in this case, I can actually work out 12 minus 7 is 5. So all in all, I get x is equal to 5. And remember that if I want to verify my answer, I can plug it back into the original problem. I would do 5 plus 7 equals 12, which says 12 equals 12. And since those are both the same, I have a true statement, which means I correctly solved for x equals 5. Number 4, very, very similar. We have x plus 9 equals negative 15. I'm again going to start by just being organized and drawing a vertical line through my equal sign. It says x plus 9. I want to get x all by itself, so I do the additive inverse of 9, which is minus 9. The 9's on the left side cancel to just give me x. And on the right side, negative 15 minus 9 is negative 24. And again, if we want, we can plug negative 24 back in and see that we do in fact get negative 15 equals negative 15. Number 5, same idea. Now we just have fractions. Okay, fractions are never going to go away, guys. You just got to get used to that. We have x minus 1/5 is equal to negative 27 over 5. We have x minus 1/5. So we're going to do the opposite, which is adding 1/5. That leaves us with just plain old x on the left because the positive 1/5 and the negative 1/5 cancel each other out by design. And on the right side, we have negative 27 over 5 plus 1 over 5. That's going to give me negative 26 over 5. Okay, we had a negative 27 and a positive 1 on top. So together, negative 26. And that common denominator just stays 5 on bottom. Notice, by the way, negative 26 over 5 cannot be reduced. So I'm just going to leave it just like that. Number 6 is almost the exact same problem, but we don't have a common denominator. So it's one step harder. We're going to do the same basic principle where since we have x plus 1/3, I'm going to do minus 1/3 to move this 1/3 to the other side. That leaves me with x on the left, and on the right side, 1/4 minus 1/3. That's not so bad. Okay, there's nothing wrong with this, but I can't leave that as my answer. So I need to find a common denominator so I can actually put these together. In this case, we have a 4 and a 3 on bottom. So 12 is going to be our least common multiple, or our lowest common denominator. When I convert to fractions with 12 as a denominator, I will have 3 over 12 minus 4 over 12. Working out that subtraction gives me negative 1 over 12. And so the solution to this problem is x equals negative 1/12. Now, you're probably very tempted to plug that back in, and rightfully so. It's a little bit more tedious in this case, though. And what you're going to realize the deeper you go into math is that it's not always that easy to plug your answer back in. It's always doable. Let's be clear, you can do it, but it's not always convenient. And so as you keep solving more and more equations, the hope is that you build up more and more confidence and that you're able to check your individual steps instead of always having to plug an answer back into the beginning equation. In this case, though, I could just take negative 12, plug it in right here for x, and I'm going to see that both sides do equal 1/4. So it works just as well as anything else. It's just not always super convenient when your answers end up being a little bit complicated. And by complicated in this case, I just mean fractions. See, I think they're complicated too, don't worry. All right, last thing we're gonna do. When we get to the next lesson, we're gonna be solving two-step equations. And some of them will have actually more than 2 steps, so it's a bit of a deceiving title. But essentially, moving terms will almost always be step 1, and making the coefficient of the variable 1 will almost always be step 2. So what we're about to do is usually the second step in the process, but for all of these problems down below, it'll be written as the only step because we don't have to do anything else. So just know that normally these 2 steps work together. All right, let's look at it. We're going to use the multiplicative inverse to make the coefficient of the variable 1. The reason we're going to do this is if you look at number 7, it says negative 5x equals 45. We don't want negative 5x, we just want 1x. So our job is to turn the number in front of the x, the coefficient, into a 1. The way we do this is by using the multiplicative inverse. So if we look at ax equals b, okay, I'm going to rewrite it slightly lower just so I can write some things around it. ax equals b. We do not want ax. We want x. So no matter what number we happen to have in front of x, we can always get rid of it by simply using the multiplicative inverse, which if you recall is the reciprocal. So if I multiply ax by 1 over a, what's going to happen is that the a on bottom will cancel out the a on top, because remember ax is really ax over 1. Everything is a fraction over 1, even if we don't write it. So again, the a on bottom cancels the a on top, and that just leaves us with x, because the a's go away. I'm not allowed to do that only to one side though, so I then have to also multiply the other side by 1 over a. Notice that we have b, which is really b over 1. So the b is on top, the a is on bottom. That just leaves me with b over a. So if ax equals b, x is equal to b over a, which is what we have on the other side of that equation up top. So the moral of the story here is whatever the coefficient of the variable is, you just multiply both sides of the equation by the reciprocal of that coefficient. The other option is to divide by a on both sides. So real quick, I'm going to delete my work and show you that one. Sometimes this is easier, sometimes not. Essentially, the rule is that if there's fractions involved, you should use the reciprocal. But if there's no fractions, then it's usually easier to just divide. So for this same thing, if I just write a line and then an a underneath on both sides, this is going to accomplish the same goal. Where on the left, the a's will cancel each other out to just leave me with that letter x. And on the right side, I just have b over a. So we are going to use that method for number 7 and number 10, but we're going to have to use a slightly different method, the first one I showed you with reciprocals, for numbers 8 and 9. All right, that being said, we got one more thing to talk about before we solve these problems. If x over a is equal to b, then x equals b times a. The quick way to view this is by just multiplying both sides by a. So I'm going to show you that one first. If I take x over a equals b, and I just multiply times a on both sides, then on the left side, we have a on top and a on bottom, so we're just left with x. And on the right side, b times a is just b times a, nothing else to it. So we can definitely do that. We can multiply by whatever is on the bottom of x. Alternatively, though, we can view this just slightly differently, and this is mathematically equivalent. Instead of x over a, I can think of it as 1 over a times x is equal to b. So x over a and 1 over a times x, exact same thing, because that x is still on top, even if I write it on the side. Now, if I view it like this, the way I solve for x is the same way I did it on the left side originally. I can multiply by the reciprocal of 1 over a, which is a over 1, and I do that on both sides. On the left side, the a on top and the a on bottom cancel to just give me x. And on the right side, b times a over 1 is just b times a. So we end up with the exact same thing either way. I encourage you to multiply by the reciprocal whenever possible, but as you're going to see again in number 7 and 10, sometimes it's more convenient to just do division. So it really is just based on context, whichever one is easier. All right, let's actually do these now. Number 7, we have negative 5x equals 45. When you have a number multiplied by a variable equals a number, the easiest thing to do is just divide. So what I'm going to do on both sides of this equation is divide by the negative 5 that is in front of the x. Notice that whatever the coefficient is, I divide by exactly that value. I'm not dividing by positive 5. I am dividing by negative 5 because I take the whole thing in front of the x and divide both sides by it. Now, a mistake I see all the time is students want to divide by the whole thing, negative 5x on both sides. That doesn't work though, because if I divide by negative 5x, the x's would also be canceling each other out, and we don't want that. We just want to get x alone, and to get x alone, we divide by its coefficient. So when I divide by negative 5 on both sides, I am left with x on the left, and on the right side, 45 divided by negative 5 is negative 9. Not a whole lot to it when we actually get used to it, but at first, it's tough to know what to do. And again, make sure you don't write x in that denominator, because then you are canceling your x out from the left side, and we want to leave x there. All right, number 8, we have x over 6 equals 9. You could multiply both sides by 6 right here, and that would give you x equals 54. There's nothing wrong with doing that. I'm going to encourage you, though, just for sake of keeping things consistent, if you rewrite this as 1 over 6 times x equals 9, that is exactly the same as x over 6. I just put the x on the side. Then I can multiply both sides by the reciprocal, and it'll just make things feel a little bit more consistent. So if I multiply both sides by 6 over 1, remember that 9 is really 9 over 1, so I can put that 1 on bottom. On the left side, these 6's cancel, so I'm just left with x. And on the right side, 9 times 6 on top is 54. 1 times 1 on bottom is 1. So I'm just left with 54, which is the same thing I would have gotten if I just multiplied both sides by 6. So either way is fine. Just make sure you're practicing both ways. Number 9 is going to force us to use the reciprocal method because I could, let's be clear, just like I did in number 7, I could just divide both sides by the coefficient of x, which in this case is 3 over 4. But I do not want to divide by a fraction, because if you divide by a fraction, you're going to have to multiply by the reciprocal anyway. So why not just go straight to multiplying by the reciprocal and save ourselves the time? I'm going to rewrite it just for sake of space here, but I have 3/4 x equals 12, so I'm going to multiply both sides by the reciprocal of 3/4, which is 4 over 3. Remember, 12 on the right side is really 12 over 1. So now when I multiply 4/3 times 3/4, the 4's cancel and the 3's cancel. That's the whole point of using the multiplicative inverse, aka the reciprocal. So we're just left with x on the left. And on the right side, I have options. I can either do 12 times 4 to get 48 and then divide by 3 to get 16. Or I can think of it as 12 divided by 3, which is 4, and then times 4. Either way, though, I get to 16. So whichever way you prefer, but 16 in the end. Number 10, I have 0.2x equals 7. This is one where students and I disagree all the time, not on the answer, but on the easiest method. Almost every student, when they see this problem, will write division by 0.2. And that is perfectly fine. Okay, if we divide both sides by 0.2, I'm going to get x on the left. And on the right side, you may have to bust out a calculator to work that out, but it's going to come out to 35. There's nothing wrong with doing it that way, but we're going to think a little bit deeper for a second. Okay, again, nothing wrong with dividing by 0.2. That is a perfect method. Our goal here is to get x by itself. And to get x by itself means we want there to be one x. So if the goal is to make the coefficient of x 1, dividing by 0.2 does that job, but it's kind of messy. I don't love the idea of dividing by a decimal, especially because this is pretty easy to make 1. If you think about it, 0.2, that's just 1/5. Okay, so if I had written this as 1/5 x equals 7, I don't think any of us would divide both sides by 0.2. I think almost all of us would multiply both sides by 5, because 5 is the reciprocal of 1/5. So if I do 5 over 1, which again is just 5 on both sides, on the left side I get x, on the right side I get 35. That is the exact same answer as what I had before, but I'm willing to bet that when I did it the first time, you guys just took for granted that 7 divided by 0.2 actually is 35. When I do it using fractions, you all know that 7 times 5 is 35. There's really no ambiguity there. So I'm not saying this method is better. I'm not saying there's anything wrong with dividing by 0.2, but recognize that in math, there's almost always more than one way to get to an answer. And our goal as mathematicians is to be efficient. And efficiency doesn't always mean the same thing, but it pretty much always means doing less steps and thinking less hard. And in this case, the easiest way to do this question, in my mind, is to multiply both sides by 5. I think that doing 7 times 5 is a whole lot easier than doing 7 divided by 0.2. But we're all different people. We all get to make up our own minds. I just hope that as you guys are practicing, you're thinking about your options, you're trying different techniques, You're checking your answers in the keys I provide you, and I hope you're learning and enjoying. And if you're doing that, then I will consider this class a success, and I look forward to seeing you in the next episode.